I want to discuss for a minute the graphical meaning of position, velocity, and time. What I have here is a graph of velocity versus time. And remember, the velocity is the derivative of position, so position would be the integral of velocity. Acceleration is the derivative of velocity, and velocity is the integral of acceleration. So here, if I want to move from down this line, from position to velocity to acceleration, I take derivatives. I'm finding the slope. If I want to move up the line, I take integrals. We're going to use that to try and understand and derive some really useful formulas to understand kinematics. So now let's talk about graphs of position, velocity, and acceleration versus time. Let's take the simplest possibility, namely that we're at a constant position. So we have a constant position like this. Then the question becomes, what would the velocity look like? Well, the velocity is the derivative of the position versus time graph, or simply the slope of the position versus time graph. But if you look there, it's pretty obvious that the slope of that graph is 0. So, if I wanted to sketch the velocity versus time, I would just draw a horizontal line at 0. And if I want to sketch the acceleration as a function of time, that would also be 0, because 0 is also a constant. And the derivative of a constant is 0. Alright, so that wasn't very interesting. If the position is constant, the velocity and the acceleration are also constant. But now let's ask the question, what would happen if instead the velocity was constant? Get my black pen back out, and I'll draw position versus time, velocity versus time, and acceleration versus time. And we're going to suppose that we have a constant velocity. Alright, well, acceleration is the slope of the velocity versus time graph. So the slope of this graph is still 0, it's constant, its derivative is 0. So as far as acceleration goes, acceleration is still going to be 0. However, things get more interesting when we find the position. We know that we're looking for a graph whose slope is the velocity. Well, that's a constant upward slope. So if I were to draw a constant upward slope, it would look something like this. Of course, there's many different places I could start. Any one of these lines has a constant upward slope. It turns out all of that information shows up in the calculus. Let's suppose we take a constant velocity and we integrate it. Then the position equals the integral of the velocity with respect to time. If I integrate that, I'm going to get, velocity is just a constant, so that stays there. The integral of dt is just time. And then I need to put plus c. Well, this plus c simply tells me, where am I at the beginning? If I were to put in time t equals 0, I would say x of 0 equals, that means at time 0, v times 0 plus c. This just cancels out, and my constant is simply the position at time 0. So all this is saying is that the position is equal to the position at time 0 plus vt. Because I had a positive v, I have these positive slopes. If I had had a negative v, it would have been a negative slope. And these different lines come from all the different positions where I can start with this same exact velocity. Now the next thing to do is to consider what would happen if we had a constant acceleration. Position versus time. Velocity versus time. Acceleration versus time. So if I have a constant acceleration, velocity is simply the integral of acceleration. And so I would be able to integrate this just as I did before and get, just as I integrated velocity to get position before, now I can integrate acceleration to get velocity. So the velocity should be a nice straight line like that, or perhaps down or there. And the equation is simply velocity is equal to the initial velocity plus the acceleration times time. Now, I'll leave the deriving the actual formula for the position versus time in this case until later, because there's a number of different things that can happen. But let's imagine, and just think of it in terms of slope. We know that we're looking for a graph whose slope looks like one of these velocity curves. Well, let's start with this one. It appears to start at about a velocity of 0, which means our initial slope should be 0. And then the velocity increases, meaning the slope increases. So that should curve upward like this. If I used the bottom one, that starts with a downward slope because it has a negative velocity, so the position starts with a negative slope, curves up until right around here it has a 0 slope, and then it continues to increase its slope like that. So notice in this case, if the acceleration is constant, the velocity is a straight line, explained by this formula, and the position is a parabola. The initial slope, we don't know just from the constant acceleration, because the initial velocity was arbitrary, and that determines the initial slope. But it does curve upward because I have this positive acceleration. All right, so let's review that one more time. If I have a constant position, then the velocity and the acceleration are each 0. When I have a constant velocity, that means the acceleration is 0, but the position is changing linearly. If it's a positive velocity, the position will be increasing, sloping up. If it's a negative velocity, the position will be decreasing or sloping down. And if I have a constant acceleration, that means the velocity will be increasing or decreasing linearly. It'll be a straight line. And the position will be a curve, some kind of a parabola. And the initial slope will depend on the initial velocity. And whether it's sloping or curving up or down will depend on whether the acceleration is positive or negative.